Hi, ladies and gents. This time we're going to spend a little time talking about Newton's universal law of gravity. Back when we were talking a little bit about Sir Isaac Newton, we mentioned this as one of his big accomplishments in his life. And Newton is the gentleman who told the story about being in the apple orchard, kind of contemplating what force was holding the moon next to the earth. And at that moment, an apple fell, and he had kind of a eureka moment in his mind, and he said, it's the same force. Now, this is not a terribly exciting story. Man in an orchard and an apple falls to the ground. That is not one of those wow, cool stories that should perpetuate for hundreds of years. But it does. And the reason the story is important is because Newton's universal law of gravity is so important. It was the very first time that someone came up with a scientific rule that governed both the heavens and the earth. In Newton's time, back in the 1700s, it was considered that the heavens were the realm where God or gods lived, and man lived on the earth. And they were two separate places, and they were governed by different laws. Newton said, nope, same thing. Same rule of gravity holds the moon that holds the apple. So that was a big, big deal. The other reason this was such a big deal is this is the first time someone mathematically explained a force field, a force that acts at a distance. And that eventually led to our understanding of things like electric fields, magnetic fields, and other situations like strong and weak forces. This is considered by many people the first grand unification of physics, when different things were joined together and the universe was coming more and more understandable. So what exactly is Newton's universal law of gravity? Now, a law in science is very often an equation, and it's an equation that explains how nature behaves. So this is Newton's universal law of gravity. Copy that down, put it on your formula sheet. Fg is our force of gravity in newtons. We've used many times. Big G is the universal gravitation constant, and that's 6.672 times 10 to the negative 11th Newton meters squared per kilogram squared. You're going to need that number every time you do a problem with this equation. M1 and M2 are two masses. You always have to have two masses to calculate the force of gravity between, and r is the radius. Now, when we do some gravity problems, radius is always measured center of mass to center of mass. It's not outside edge to outside edge. One of the reasons Newton had to invent calculus is the fact that he had to prove that you could pretend all of the mass of something like the Earth was located at its geometric center, and all of the mass of the moon could be mathematically treated as if it was at the geometric center. And if those two things were true, then you could calculate the force of gravity center to center. So what does this law of gravity say? This Fg equals big G mass 1 mass 2 over r squared. Well, it says a whole bunch of cool things. One, it says there always is a force of gravity between any two masses. Right now, there's a force of gravity between you and your computer, between you and your coffee cup, between you and your pen. There's also a force of gravity between your pen and your coffee cup. If an object has mass, it exerts a force of gravity. So all masses are gravitationally attracted to all other masses. Well, if that's true, why don't everything just glom together in a big pile someplace? Why doesn't your pen just kind of go and suck to you, and your coffee cup end up wearing that on your sweater or whatever? Why are we able to have things that are separate if they're constantly attracted to each other? Two reasons. One, gravity is the weakest of the four fundamental forces. So when you fall sometime and hurt your knee, that feels like gravity is a big force. But of the primary forces, gravity is the weakest. The second reason why everything does not glom all together is due to the fact that there is one overwhelming mega force of gravity vector that you and I live in the middle of, and that's the force of gravity between you and the Earth. And so there might be little forces of gravity left, right, and center, but they are so puny compared to the massive force of gravity that you and I are experiencing because of our planet. Back to this idea of why don't things kind of glom together, they actually do. If you have particles of dust in deepest, darkest outer space, slowly over time, they will all cluster together, and those little micro clusters then cluster together, and it's by that clustering of particles that we end up with things that have slightly larger gravity because they have more mass to them than individual particles of dust. And slowly over time, that's how you build a star, or that's how you build a planet. One of the other things that force of gravity equation says is force of gravity is dependent or proportional to mass. So the mass of something has a big influence on the quantity or the amount of gravity it's going to produce. Something small like a puppy is going to have a small force of gravity. Something bigger like planet Earth, big force of gravity. Something many, many times larger like the sun is going to have a humongous force of gravity. So massive things, big force of gravity. Little things, little force of gravity. Now, force of gravity is also proportional to 1 over the distance between the centers squared. What does that mean? This is called the inverse square law. And it says that gravity gets weaker with the inverse square of the distance between the centers. So here's what I'm talking about. If you were standing on the surface of the Earth, you would have a weight of 1 force of gravity. So let's say that you weighed 1,000 newtons. Right? If I could put you in a spaceship and zoom you out so you were 2 radii from the center of the Earth, twice as far from the center, your force of gravity would fall down to 1 over 2 squared, or 1/4 of what it was on the surface of the Earth. If I could zoom you out 3 radii from the center of the Earth, the force of gravity on you would be 1 over 3 squared, or 1/9. 4 radii, 1 over 4 squared, 1/16, and you can keep doing that till you're silly. All force fields follow this inverse square law. Magnetic force fields, electric force fields, and so when you get to those topics, remember that idea. Here's another way of looking at it. If I graph force of gravity here, versus radii here. If I'm standing on the surface of a planet, let's say the force of gravity on me is 100, let's call this 50, let's call this 25, etc. If I move to 2 force of gravity, my 2 radii, my force of gravity is going to be 1/4. If I move to 3, it's going to be 1/9. 4, it's going to be 1/16. 5, it's going to be 1/25. And if I draw this graph, here's what you're going to notice. This curve is going to get weaker very, very quickly in the beginning, but will this line ever reach 0? No, it never actually goes to 0. So what does that mean? Gravity, as far as we understand, has a range that is infinite. There is not an edge to where gravity stops acting. It will get really weak over time, but it will keep going on. Let me give you a couple examples. Pluto has a period of rotation somewhere around 256 years. Well, that is about back to the signing of the Declaration of Independence, 1776. Since the signing of the Declaration of Independence, Pluto has gone through not quite 1 complete year. Pluto is so far away. It is somewhere around 3 billion miles away. And yet the force of gravity from the sun on Pluto is strong enough to hold Pluto in orbit. Here's another weird and crazy thing. We are in the Milky Way galaxy. The Milky Way galaxy, the next closest galaxy to us is the Andromeda galaxy, which is 2.5 million light years away. What that means is if you take a flashlight and you shine it up at the Andromeda galaxy, it would take 2.5 million years, okay, 2.5 million years for the photons of light to actually hit Andromeda. And yet, even though these two galaxies are so far away, we are actually colliding between the Milky Way and the Andromeda galaxy. They're gravitationally being drawn together. When will they hit? In about 3.75 billion years, so don't lay awake nights worrying about it. That's a long time in the future. But the math says we are moving towards each other at a pretty good speed. All right, that will finish our force of gravity, and we'll come back and talk some more about it later.